All right, so we want to evaluate this integral. This is an improper integral of a real valued function. And we want to notice right away that this function, we're going to call this f of x, this guy is even. And so that tells us that if the Cauchy principal value of this integral exists, then the value of this improper integral will be equal to the value of the, will be equal to its Cauchy principal value. So that's what we're going to focus on. And so we're going to consider f of z equals z squared over z to the fourth plus 1. And we're interested in where the singularities are for f of z, where are the zeros of the denominator. And so we're going to set z to the fourth plus 1 equals to 0. We're going to solve. And of course, we're just going to get the fourth roots of unity. You guys know how to do that. Why don't you pause the video, actually, and work out those 4 solutions yourself. It might be a good review for you to go back and make sure we can do that. But here they are. We're going to get 1 plus I over root 2, 1 minus I over root 2, minus 1 plus I over root 2, and minus 1 minus I over root 2. And so we're interested in the zeros that live above the x-axis. So certainly we're going to have 1 plus I over root 2 somewhere over here. Let's just say that it's right there. And then on the other side, we're going to have minus 1, minus 1 plus I over root 2 over here. So those are the 2 zeros that live that live above the x-axis. We could plot the other 2 down here, but I don't need those. So, okay, at this point, I know that the integral over c of my function f of z dz is just 2 pi I times the sum of the residues. So the residue of f at, let's call this guy z1 here, and we'll call this one z2 there. Okay, so this is the sum of the residues of f at z equals z1 plus the residue of f at z equals z2. So I've just about got the value of the integral of f around the whole curve. Let's go ahead and compute the residues now. This is a long problem. These are multi-step problems. So for the first residue, let's just see how it goes. We're going to use the theorem that we did at the beginning of this lecture. So the residue at z equals z1, I'm going to realize that this is exactly z squared over the derivative. We said the derivative of the bottom. And then we said, look, you need to plug z equals z1 into the whole thing. So you're plugging z equals z1 into the numerator over the derivative of the denominator. And so this works, by the way, because when you plug in z1 upstairs, you don't get 0. When you plug in z1 downstairs, you do get 0, but when you plug z1 into the derivative, you're not going to get 0. Please check all of that. And so let's work this out. So this is equal to, this is equal to z squared over 4z cubed evaluated at z equals z1. Cancel the z's. This is just 1 over 4z evaluated at z equals z1. So I'm going to go down over here and say, okay, well, this is exactly root 2 over 4 times 1 plus I. I'm just plugging in my z downstairs, the root 2, flip it up. And so we want to put this in standard form, and so you can write this as 1 minus I over 4 root 2. That's the residue of f at z1. I'll let you work out on your own. Please pause the video. You can compute that the residue of f at z equals z2 is minus 1 minus I all over 4 root 2. So please check that using the same techniques. And so the point is, if we go back here, the integral of our function around the entire arc is 2 pi I times the sum of these 2 residues. Well, look, when you add these together, you're going to cancel the 1s, and you're just going to get a minus 2i upstairs over 4 root 2. The i's and the negative are going to cancel, and you're going to end up with what? You're going to end up with pi over the 4. The 4's are going to cancel, so pi over root 2. So let's stop this video here. This is the first part of the problem. The first part of the problem is you compute the value of the integral of your complex function all the way around the closed contour. Then in the second part of the problem, you study the different pieces. And we're going to know that this piece is going to go to the improper integral of a real function that we want. And then this piece we're going to try to show goes to 0, giving us the answer that we want. So next video we'll look